To understand the force and energy in a spring, we have to be familiar with a few simple equations. The first one is simply known as Hooke's law, which is that the force in a spring is equal to negative k times delta x. In this equation, the k is simply referring to how thick or stiff is the spring, or in other words, how hard is it to stretch and squish the spring. The delta x is simply referring to how far the spring squishes or bends from a point of equilibrium. In this case, on the left, we do have a weight pulling down on the string, but since the spring is not actively moving, it's just hanging there motionless in space, we still call that a point of equilibrium. So the delta x is simply how far we pull the spring down when we tug on the weight with our hand. When you apply a force to a spring, you're also creating potential energy, because eventually that spring is going to want to return back to its point of equilibrium. And when it does that, it's going to cause whatever is attached to the spring to move. The equation we use to measure the potential energy in a spring is simply 1/2 times the spring constant times how much we moved it squared, or 1/2 kx squared. So the spring gets compressed, and then the spring is allowed to expand. And when it expands, it moves an object quickly into the air. The object that is moved by the spring now has its own energy. Since it's moving, it has kinetic energy. And we measure kinetic energy with 1/2 times the mass of the object times the velocity squared. Now, eventually that object will stop going up, and it will pause momentarily before it starts to head back down to Earth. At its maximum height, the object also has its own potential energy, and that energy is simply equal to its mass times its gravity times its height. And then the object will begin to fall back down to Earth, and right before it hits the ground, it will reach its maximum velocity. And at that point, all of the potential energy, all of the mgh, has been converted once again back into kinetic energy, or 1/2 mv squared. And in this cycle of spring energy to kinetic energy to potential energy and back to kinetic energy, all of these equations are the same. So 1/2 kx squared is equal to 1/2 mv squared, which is equal to mgh, which again is equal to 1/2 mv squared. So here's a relatively simple equation. We have a spring, and we're talking about how far is this spring going to be compressed. So naturally we're talking about the equation, our force is equal to our negative k delta x. And the negative sign really isn't that important. Usually in physics, a negative sign simply refers to something going to the left or going down, as opposed to going to the right or upward. So most of the time you can simply remember your equation as k delta x. So we have a force of 40 newtons pulling down. We also have a mass of 5 kilograms that's also attached to the spring. The 5 kilogram weight is going to pull down on the spring with a force of, or 5 kilograms times 10 for gravity. So our combined downward force is the 50 newtons we get from the mass, plus the 40 newtons we get from our hand pulling on the spring, for a combined force of 90 newtons. Then we just simply plug it into our equation. 90 newtons is equal to our k of 200 times our x that we don't know yet. If we do some math, divide both sides by 200, we get x is equal to 9/20, which is roughly 1/2 or 0.5. The only thing to be careful about here is that your spring constant is presented to us in meters, and the question is asking about centimeters. So we just have to convert meters into centimeters, and we do that by multiplying by 100. 0.5 times 100, and we get 50 centimeters. In this problem, we're compressing a spring and then launching some objects into the air, which means we're really converting the potential energy in the spring into the potential energy the blocks will have at their maximum height. In other words, the potential energy in the spring, which is 1/2 times the spring constant times how far we compress the spring squared, is equal to the mass of the objects times gravity times height. The temptation is to think that because blocks A and B are not the same size, that one block will travel higher or faster than the other. But this is not true, because both blocks are attached to the same spring, which means they will accelerate upwards at the exact same rate, and then once they leave the spring, gravity slows all objects, both heavy and light, down at the exact same rate. So our equation then becomes 1/2 times a spring constant of 4,000 times 100 centimeters, which I write as just 1 meter squared, that is equal to a combined mass of 15 times gravity of 10 times a height that we don't know yet, or 2,000 divided by 15 times 10. That's going to be my height. Some zeros cancel out, and I'm left with a height that is equal to 200 divided by 15, which you could approximate to be roughly 13 or about 13 meters.